Hello, today I'll be introducing my MC1R protein model, which stands for melanocortin-1 receptor. The MC1R is found on the plasma membrane of melanocytes, which are specialized skin cells responsible for producing pigment. Its main role is to control the type and amount of melanin produced in the skin and hair. When MC1R functions normally, it increases the production of melanin, a dark pigment that protects us from the UV radiation. Mutations like MC1R are linked to red hair color phenotype, fair skin, freckles, and a higher risk of skin cancer, especially melanoma. So because of this, the skin has less protection against UV damage. So overall, the 3D shape of my protein, the MC1R is a G protein coupled receptor, which has a distinctive serpentine shape, meaning it weaves back and forth through the cell membrane. It has 7 transmembrane alpha helixes that cross the membrane, and overall arrangement, these helixes form the core structure of the receptor. For my model, I use pipe cleaners to represent the 7 alpha helixes. However, in my model, I showed 5 because I wanted to emphasize the mutation between alpha helixes 3 and 4. I arranged them on like oval formations, inserting them on the foam board, which represents the cell membrane. And I connected more pipe cleaners in the intercellular side to show the intercellular loops. And then you can see here between between alpha helixes 3 and 4, where the mutation site at position 151 occurs. So the MC1R protein includes several levels of structure. Its primary structure is a sequence of amino acids in the polypeptide chain. The secondary structure is made up of alpha helixes, which you can see here. The tetraisomer comes from folding of the helixes into a 3D receptor shape across the membrane. However, this specific protein structure does not have a quaternary structure because it's a single polypeptide chain. But it does interact with other molecules like G proteins when it's active. And I don't know if you can see here, this is where I represented the G protein intercellularly. MC1R doesn't contain separate subunits, but it does have different domains, such as the extracellular loops that bind to the alpha MSH hormone, which is represented up here by the M terminus, and the intercellular loops that interact with G proteins to pass through on signals inside of the cell. So in my models, I showed this with different colors in the pipe cleaners, making it easy to see. How I represented each structure: for my primary structure, I represented the mutation marker that occurs right here, indicating a specific amino acid change. So the second structure is my alpha helixes made of pipe cleaners, and the tetrary structure, through the way the helixes are arranged and come across as 3D in the membrane. And like I stated before, the quaternary structure doesn't apply. How my mutation affects the structure: my assigned mutation is R151C, which is a change from argan to cytosine at the amino acid position 151, located on the second intercellular loop, but it occurs between the third and fourth intercellular loop. Argon is a large positively charged hydrophilic amino acid that helps stabilize a loop and interact with other proteins. However, because of this mutation, when it's replaced by cytosine, which is a smaller and more neutral amino acid, it can form disulfide bonds, and this can cause the loops to become unstable. I chose to build one model to represent the MC1R mutation site because rather than the 2 models, this allowed me to highlight where the mutation occurs and talk about how it changes the protein structure and function. How this mutation affects MC1R: it makes the cell signaling less effective. This means that melanin is produced in more faux melanin, which is bright red or yellow pigment. At the cell level, melanocytes produce less UV protective melanin. At the organized level, this results in people having red hair, fair skin, and increased sensitivity to sunlight. So over time, lack of protection increases the risk of sunburn, skin cancer, and especially melanoma. Limitations to my model was, obviously, to scale, the model is millions of times larger than the MC1R protein. The model is static, but in reality, the MC1R protein moves and changes shape when it binds to ligands in activates G proteins. In molecular detail, my model doesn't show that actual molecular interactions such as hydrogen bonds and ionic interactions between amino acids or how the protein sits in the fluid lipid bilayer. So thank you for listening to my MC1R protein presentation.